If I can step into your camera view for a moment, I will introduce you. So I am Rebecca Wright, and happy to introduce today our speaker, Miguel Mosteiro, who will be talking to us about polynomial counting in anonymous dynamic networks, as well as its applications to anonymous dynamic algebraic computations. Miguel is an associate professor at Pace University in computer science. Before that, he was at Keene University. Also, he was at Rutgers for a while. I was also at Rutgers for a while, and we just established that he left shortly before I arrived. So we didn't get to know each other there, as well as he was a research fellow at the Universidad de Juan Carlos in Spain. He got his PhD from Rutgers, and his research interests span the broad areas of algorithms and distributed computing, with a lot of focus on practical applications as motivating scenarios, so restricted wireless networks, cloud computing, crowd computing, spammability, fairness in algorithms like PageRank. And he received the 2016 Keene University Undergraduate Research Mentor of the Year Award, as well as his student at the time received the Undergraduate Researcher of the Year Award. So, so lots of experience, good experiences working with undergrads, and very happy to have him with us today.
Well, thank you, Rebecca, for the nice introduction. And actually, that award was for a seminal work of this work that I'm presenting today. So thank you for attending. This is joint work with my colleague Dariusz Kowalski, who at that point when we started, he was in Liverpool, now he's in Augusta. And now I'm not able to move to the next, for some reason, sorry. I'm not able to move to the next slide. My computer just crashed.
Okay, figure that one.
I don't even have it. Oh, let's see. There you go. Hopefully. Anonymous dynamic networks is a model that recently, let's say in the last 10 years or so, attracted a lot of attention from algorithms people because of its challenges. The motivation, I mean, one of the possible applications of such a model is, for instance, wireless sensor networks embedded in the Internet of Things. That is just one model. It could be used. The same model could be used in many other settings. The model is the following: we have a network, communication network, with a fixed set of nodes, n nodes. The nodes do not have identifiers or labels. They are all indistinguishable due to, for instance, massive, I mean, if the network is massive or maybe impractical or not cost effective to put identifiers, unique identifiers in each node. So in this model, we just assume that there are no identifiers, that the nodes are all identical, except for one, which is a special node, which we sometimes call the leader. Now we are changing that name, which was shown in 2013 already by Michail Chatzigiannakis and Spirakis in a seminal paper on this topic, that is needed. We cannot solve deterministically the counting problem without a distinguished node. So given this fixed set of nodes, the communication is synchronous. All the nodes start at the same time and communicate among them synchronously through links in any given round. So we divide time in rounds of communication. In any given round, a node broadcasts a message to all neighbors and receives a message if needed. I mean, if the neighbors send a message, receive a message from the neighbors, and execute some local computation whose time we consider negligible. So we just, as a time complexity measure, we count the number of rounds of communication. And the messages in some other work, not in this work, other works, we also count the message complexity, the number of messages that they exchange. We assume connectivity, in terms of connectivity, we assume the model called one interval connectivity by Kuhn and others. Links may change from round to round, adversarially. But we guarantee that the network is connected. And at any given round, the network has to be connected. But the links may change arbitrarily. So it's completely dynamic, except that we require connectivity in each round. That's the basic anonymous dynamic networks model, which now is changing in some aspects.
But you assume that synchronous communication is atomic. It's not changing structure like within the round. The messages the neighbors receive and the neighbors messages.
If this is the snapshot in a given round, this node is able to pass a message to all these nodes and receive messages from all these nodes and execute some local computation. It's reliable. The communication is reliable. We may have a MAC layer behind or something to ensure the communication, but the challenge is in the dynamicity. From round to round, then the links may change arbitrarily. So that is what makes basically the counting problem difficult. Counting problem is just to know what is the network size, right? Nodes need to know this to execute more complex computations. Termination usually in distributed computing is decided with a function of n, of the number of processors participating. And so if we don't know n, for many, many distributed algorithms, we cannot decide when to stop. But the network the model is well, I mean, it fits well applications where the number of nodes is massive. You can think of nano networks, for instance. We are actually working on a proposal, an NSF proposal in nano networks. Nano networks where you have a massive number of nodes and you don't know in advance how many are they going to be. So in such a setting, how do you count the size of the network? How do you count the size of the network if nodes are not distinguishable and they basically, it's like mobility could be the reason why the dynamics, right? They change positions all the time. Well, as I said, in distributed algorithms, we need to know the number of processors, and so we need a protocol, and that does the following. Given a system of n nodes, all nodes eventually terminate knowing n. This is an overview of previous work. As I said, there was a lot of excitement on this problem. It's a very simple problem on a very challenging setting. And that makes it, I would say, I used to say the algorithmicist delight, right? Because it's difficult, but very simple, seems simple. And in the seminal work by Spirakis and his colleagues, they guarantee an exponential upper bound on the network size only. So they compute the network size, but it's only an upper bound, and it's even could be as bad as exponential, which is of course very bad. And they guarantee the exact size, but it's doubly exponential in the number. In terms of rounds of communication, it's doubly exponential, the function. And it takes exponential number of rounds. There are others that takes exponential number of rounds, but do not terminate. They continue running forever. And others terminate, but they don't give running time guarantees. So eventually, we know that the protocol stops, but they don't have running time guarantees. More recently, well, it's not that recent anymore, it's 2015, I visited Alessia Milani in the University of Bordeaux. She shared this problem with me. And we started working on it. And after a week, we came up with this new protocol, incremental counting, that takes polynomial space and it achieves an exponential speed up. It computes the exact count, the exact number of nodes, but with exponential running time. Whereas the previous one that didn't use anything and obtained the exact count was doubly exponential. So it is an exponential speed up, but it's still not practical. And it needs to know the dynamic maximum degree. I put dynamic there because remember that the links change, so the degrees change, and we just consider the maximum degree that any node could possibly have throughout the computation. It needs that information, and but it was an interesting step. Based on this work, I had my student Maitri Chakraborty at Kane working in simulations, and that was what got her the award. And we saw in many very standard topologies, random graphs, stars, trees, and so on, that the algorithm was actually running in polynomial time for most of this, for all of our experiments. So it was a promising line trying to improve the running time from exponential to polynomial. There was also another work that was obtaining similar findings, but with exponential space. We didn't want to use exponential space for obvious reasons. On the other hand, for lower bounds, only the trivial lower bounds are known. And that is still a fact. That is still true today. The dynamic diameter, again, it's a dynamic network, so the diameter may change, but we assume that, I mean, we can show very easily that the dynamic diameter is a lower bound. And even if the dynamic diameter is constant, there is a lower bound of log n for obtaining the network size. But these are really straightforward lower bounds. I mean, the gap is still huge with the work that I'm going to present today. In our experiment, this is the work by Maitri, where we show that it is polynomial in practice. So this is a summary. These are the restrictions or the shortcomings of previous work. You know, the algorithm may not stop, or may stop only eventually, or may compute an exponential upper bound on the network size, or may need exponential space, or so on. The first work, this was when I visited Derek in Liverpool in 2018. We worked on this problem, and we found, design an algorithm that works in polynomial number of rounds. We call it methodical counting. It is, you know, an application of a new technique modeling the evolution of the algorithm as lazy random walks. And this got us the Best Paper Award, and it was even published in the Journal of the ACM. So what are the main features of this new algorithm called methodical counting? The algorithm doesn't need any knowledge of network characteristics. It computes the exact size of the network, n. All nodes obtain n and terminate, stop. And it is the first one with polynomial time guarantees, and it's exponentially faster than the previously best algorithm. The algorithm has new control mechanisms to detect wrong convergence. The algorithm basically is gossip-based, meaning nodes share some value iteratively, and fractions of some value iteratively that we call potential, and until they reach convergence. And this is a technique that is used a lot in distributed computing because it's for reliability. It's a very reliable method of computing. But on the other hand, you need an estimate of convergence time. You need to know how many times you need to iterate on this sharing to know when to stop. If you don't know the network size, it's very difficult to know when to stop. I mean, the convergence time is normally, of course, a function of the network size. So one main novelty of the algorithm is that we included in the algorithm some control mechanisms to detect that the convergence time estimation is wrong on the fly, of course. And that is, of course, of paramount importance for counting because we don't know it. It also, we think that it also opens the path to study more complex computations using similar techniques. Indeed, now we have already 2 papers accepted, one on leader election and another one on network consensus. And basically, this is building upon this initial work. In this paper, using basically the same algorithm with some modification, we show also that we can also compute other functions like the sum of input values. Let's say that the nodes have an input value and they want to compute the sum of them or the average or the maximum. All these algebraic functions can be computed with our algorithm with the same running time. So now I'm going to give more details of the algorithm. Any questions so far? Feel free to stop me if you have questions. The key idea, as I said, is to distribute the potential value iteratively. So nodes initially have a potential We call it potential, it's just a value, 1 or 0. And they share fractions with their neighbors iteratively until they converge to some state. This is similar to previous works that have been done for this problem. But in previous works, the leader is a sink, collects all the information, all the potential during these iterations. And the problem with that is that it's difficult to analyze because there is one distinguished node. And these gossip-based algorithms usually are analyzed with as random walks, and in particular in this case as lazy random walks. They are not sharing everything. They're just keeping part of the potential. But because there was a node that it was distinguished, it was very difficult to apply these techniques for the analysis. So in this algorithm, in methodical counting, what we do is we let the leader remove potential, but only every now and then. During most of the time, the leader is sharing as everyone else. And therefore, we can leverage the previous work on lazy random walks. Anyway, it's not a simple de-randomization of a random walk. In anonymous dynamic networks, the neighbors cannot be distinguished. That's a major challenge. Even the number of neighbors is unknown at transmission time. So each node has a new set of neighbors, but doesn't know how many until it receives. But by the time that it receives, it's too late, because the next time that it needs to send something, the neighbors may be different. So, and there are no parameters of the network known, and the mixing and cover time of lazy random walks depend on n, but n is not known, so it cannot be used for termination. It's not a straightforward application of the lazy random walks analysis. So we do use lazy random walk bounds, but only while the parameters are temporarily fixed, meaning the leader participates and we try some estimate of the network size. With that estimate of the network size, we compute the bounds on lazy random walks. And if it is correct, meaning if the estimate of the size is actually n, we reach convergence of these values. But if it is incorrect, we need to detect it somehow. And that is what I'm going to explain to you now. The structure of the algorithm is more or less this one. It's conceptually divided in epochs. Each epoch corresponds to one estimate of the network size. So we have this variable k, that is our estimate of the network size. We start with 2 and we increase one by one, 2, 3, 4, and so on, up to n when we finish the computation, when it is detected that the estimate is actually n. Each epoch is divided in phases. At the end of each phase is when the leader is going to remove the potential that it has collected by this distribution of potential. And in each phase, we divide it in rounds, and we have the number of rounds is enough to reach convergence when k is actually n. So you see, the algorithm works, it's quite simple and easy to explain. For k equal to n, it's equal, I mean, you still have to prove correctness, but when you have the right k, the algorithm converges to the average, the leader collects the potential, and we are all happy. The problem is that we need to detect that k is equal to n, because otherwise anything could happen. Even the potential could grow above the initial potential. So here is a, I'm going to do a little bit of an animation with this simple network where we have 6 nodes. One of them is the leader. This guy is the leader. The others are non-leaders. And these batteries are representing the potential, which is, of course, is not energy. It's a number, right? But I'm representing it with that. A full battery is a 1. An empty battery is a 0. And the leader is trying to find out whether the estimate k is n or not. Now, at this point, I should say, maybe you're wondering, if you are distributing potential, why don't you use just the gossip-based technique of computing n by averaging 1? Meaning, if I assign a 1 to one node and 0 to all others, and I share iteratively until we reach convergence, everyone will have 1 over n. But convergence is an approximation. In these methods, in these gossip-based methods, we converge to the actual answer. We don't reach, when you could run forever without reaching the actual answer. So obtaining 1 over n approximately doesn't give you guarantees on exact network size. So we need to do it in some other way, and that's the way that we do it. We just run an estimate of the size, and we verify whether that estimate is correct or not, right, with this procedure. So let me explain now how one phase goes. We start with some potential. The nodes share a fraction of it. All nodes share a fraction of it. The leader doesn't have any to share, so only receives some fraction. The others share, and if it is the first round, so in this particular topology, they end up having the same, sharing the same that they receive, because it's the same. All are using the same fraction, which is a function of k. But it helps to understand the algorithm. It helps to think of k already being n, because then everything works nicely, and then we think what happens if k is not n. At the end of the round, after they have shared, well, the leader had gotten a little bit of potential. The others, this one, which is the only neighbor of the leader, has lost that little bit of potential. The others are the same because they exchange the same amount. By round 2, they repeat. They share again a fraction. Of course, now fractions are different. They share again a fraction, and the leader gets a little bit more. By the end of round 2, the leader gets more potential. This node that is the neighbor of the leader gets a little bit less, and so on. If we repeat this for a number of rounds, r, which is a function of k, when k is equal to n, this number of rounds is large enough to average all the potentials in them. They get to the average within some range, within some warranties.
And this is true even if it's dynamic. Like your picture didn't have the links changing at all.
Oh, yeah. Well, for simplicity of the drawing. But yeah. For this round, the links could be different, of course, yes.
The leader stays the same.
Always. Yeah. The nodes are fixed. What changes is the communication. Interestingly, the more dynamicity, well, it's not that surprising in some sense. The more dynamicity that you have, the faster that it converges. But
is there a canonical example of the kind of network that would be this, where the nodes are like, it's not that you have people coming and going. That's not what's dynamic.
A fixed set. Well, it's an ad hoc network.
Mm-hmm.
You have an ad hoc network where you deploy a massive number of nodes, and some of them could collapse. Let's say you have a chopper deploying sensor nodes on a volcano. And some of them fall on the lava or whatever. So you establish a network with the remaining nodes.
I see. But we assume once they didn't land in the lava.
Yeah. There is an assumption of reliability on the nodes.
So it's something about the initial setup is the issue here.
Yeah. We are starting with this model, which is so popular for now, but we are adding complexity of the model. Yes. All right. So this is what happens at the end of the phase. So the potential distribution that I just showed you in that drawing is this. Basically, it's just an equation, right? I take my potential, I add the potential that I received from neighbors, and subtract the potential that I shared from neighbors by that communication. And then at the end of the phase, after so many rounds, the leader removes the potential from the computation to a separate accumulator, which we call rho. And again, a new phase, and they average again, and the leader removes the potential, and a new phase, they average again, and the leader removes the potential, and so on. After enough number of phases, the leader has removed almost all the potential from the network, right, to this separate accumulator. And then at the end of the epoch, we check whether the potential accumulated by the leader is within some range that we computed. We know that if the potential is below some threshold or above some threshold, we know that the estimate k is still small. But the opposite is not necessarily true. We would like to say that if it is within this range, we know that k is equal to n, but we need some previous alarms to detect when k is really, really small, we need some previous alarms to detect that k is smaller than n. And this is just a very sketchy description of the alarms. When k is far from n, it's really small, then not many nodes in the network, and that is a threshold that we compute. Not many nodes in the network has some potential smaller than another threshold that we have to compute. And so the leader will receive the alarm of k being too small from nodes with potential above that threshold soon after the first phase, immediately after the first phase, actually. If the first phase is enough to detect that k is too small, but really, really small with respect to n. We are far from it. On the other hand, as we get close to n, the leader removes too much potential. K is still smaller than n, but it's close to n, so the leader removes too much potential and is able to detect after this number of phases. So we use those alarms and we put basically a flag that we call status. If the status is still normal, if nobody detected that k was smaller than n and the potential accumulated by the leader is within some range, the leader is enough. The leader decides that k is in fact n, and it can announce to all the nodes in n time, because now it knows n. It can just flood the network saying, "Hey, status is done. We are done. This k, everyone uses the same k because it's synchronous. So this k is indeed the network size. Otherwise, we just try the next k. We move forward to the next epoch and try the next estimate of the network size. It's more or less the idea clear. So this is our main theorem. We have the definition of the functions, the number of phases, the number of rounds, and the thresholds, and so on. When we compute, and this is the running time, when we compute the big O, we obtain n to the 5 times some log factor, polynomial. So it was great. It was the first polynomial running time, but still n to the 5 compared with the lower bound of dynamic diameter is a huge gap. So we continued working on ways of improving this. But before going there, let me quickly describe, have to be quick, describe how do we do other algebraic computations. It's quite easy. Let's say that we have to do the sum of input values. Each node has an input value, and we want to sum all of them. Again, we can use this gossip-based algorithm, but we are going to converge to an approximation of the sum, and we want the exact sum. So how do we handle it? We look at the values in its bit representation, and we compute bit by bit. Applying the same algorithm, we compute bit by bit rather than the whole number. So we append to the potential, we append the bit representation of the value. Each node appends the bit representation of its initial value. And it does that for each phase. So it resets the values. The control mechanism for deciding that we are done is still the potential. So we reset the values for each new phase to the initial values. After completing the computation of n, using the potential as a method, nodes can just compute the sum by this formula, which we show it's the actual sum, it's the exact sum. And this can be extended once we have n and the sum. Of course, it can be extended to average. It can be extended to Boolean functions on bits, right? And or XOR and so on. Some database queries, linear synopsis, and others. Same algorithm with some modifications. So this is the follow-up. We design a new algorithm that speeds up the running time by having more than one leader. In the initial one, we said, well, these people showed, Spirakis et al. Showed that we need at least one leader. But can we have more? What is exactly the information that we need to know about that, about those leaders in order to compute? So we consider more leaders, more than one, and we also improved by, of course, doing exponential exploration of k. So instead of increasing k one by one, we double k. The issue now is that k could go above n, right? We are doubling, we can go above n, so we need a new set of alarms to detect when k is bigger than n, what happens with the computation of the potential. It does require knowledge of L. We need to know how many leaders we have. But in the same paper, we all show that, in fact, that is the information that is needed in order to solve the problem. We show an impossibility result. Deterministic counting is not possible if we don't know the number of leaders. And of course, in the previous work, there was only one leader. So we knew the number of leaders. We just didn't use it because we didn't know that what if we have more. Now we were able to show that indeed what we need to know is how many leaders we have, not only a leader, how many they are. And we also showed that, in fact, no randomized counting is correct even with constant probability if we don't know the number of leaders. Because our aim was, what if we are always thinking on having an homogeneous network. We don't like to have a distinguished node, right? It was proved that deterministically, we needed to solve it deterministically, we needed a distinguished node. But in an anonymous dynamic network, it's a minus, right? It's a shortcoming to have a distinguished node. So what if we don't have a distinguished node? Can we solve the problem randomized with a randomized algorithm? Turns out that we showed also another result that it is not possible. It is not possible to solve it randomized even with constant probability, without having leaders or without knowing the number. So for that scenario, we consider a weaker version of the problem, which is called unconscious counting. Some people before divided the problem in conscious and unconscious. And basically what unconscious counting means is that the program doesn't terminate because nodes do not know if they have reached the correct count or not. We design an algorithm, we call it leaderless methodical counting, doesn't have any leaders, but nodes may be updating the network size all the time until they reach the correct one. But they don't know that they reached the correct one, so they have to continue running the algorithm on the background, let's say. You run a distributed algorithm, you start computing the network size, and then you continue from there at some point, hoping that the network size estimated so far is the correct one, but it may be updated later. How that this methodical multi-counting with many leaders compares with methodical counting is not straightforward application of methodical counting, because yes, you have many leaders, you can still use methodical counting, but once the leaders have arrived to some count, how do you combine them, right? How do they communicate? The leaders are all the same among them. They are distinguished from the other non-leader nodes, but among them, they are all the same. Even though they know how many, how do they communicate? A leader sends a message through the network, and then it receives a message. It could be its own message coming back because of this dynamicity of the topology. So we design a new set of alarms so that all the leaders can simultaneously detect k equal to n rather than having to communicate among them. And I'm going to skip the details because I don't have enough time. I just want to give you a glimpse of the impossibility result, the deterministic impossibility at least. We basically designed two gadgets, two networks of different size. The black nodes are leaders, the white nodes are non-leaders. And if you take a look, in both networks, although they have different size, each node has the same type of neighbors. Remember, the white nodes are all indistinguishable among them. Black nodes are all indistinguishable among them. So the only information that the node can gather is what type of node is my neighbor, right? Black or white. And the result applies even for static. I mean, these networks are static. We don't change the topology. Given that they have the same neighborhood, they have the same history. So we will prove this invariant, that leaders in both networks have the same history, and non-leaders in both networks have the same history, right? Of course, leaders and non-leaders have different histories, but in each group, all have the same history. Using that, we show that, let's say that T is the first time slot or round of communication in which a leader outputs N as the count of this, as the number of this network size. Then all the leaders should output N at the same time, the same N. But the N is different in these two networks, which shows a contradiction coming from the fact that nothing, I mean, the number of nodes is not known. The number of black nodes is not known. If they knew that the number of nodes, of course, very easily will know that N is correct or incorrect. Indeed, we also show a bound on approximation. It's straightforward algebra. And about the randomized algorithm, the randomization comes from basically initially each node chooses to be a leader or not. Right? We don't have leaders. The network in this network, all nodes are the same, and using some initial probability, they choose to be leader or not. Of course, the choice is stochastic, then the outcome is stochastic. We don't have a guarantee on how many leaders we have, and therefore the impossibility of applying the deterministic algorithm applies, right? We don't know what is L. L is the number of leaders. So we look at this problem, simpler problem, or weaker, I would say, called unconscious counting, that is different from the initial definition of counting, just in this part, possibly not knowing when they obtain the correct count. They still obtain the correct count, all of them, in fact, all of them at the same time, but the count may be updated. But the good aspect, I would say, of that is that in our algorithm, once the correct count is obtained, it's never changed, right? It could be in other algorithms, could be that it goes up and down. In this case, you reach the count, it never changes anymore, but nodes do not know when that happens. We show an upper bound on the running time, so we give time guarantees, but those time guarantees are functions of N, and because N is not known in advance, we cannot use that as termination. The key ingredients of the algorithms are the following. We will apply, we will apply methodical counting. We will apply methodical counting with one leader, assuming just one leader. But we don't know N in advance, and so we don't know, moreover, we don't know the outcome of the stochastic choice. We don't know how many leaders there will be there, so we don't know when to stop. And so we try powers of 2 for the number of epochs, the number of estimates that we try. So all nodes make a random choice with some leaders. We assume that there is exactly one leader. We run the methodical counting algorithm up to this capital K for L equal to 1. If the capital K is bigger or equal than N, and there is exactly one black node, by the correctness of the methodical counting algorithm, we get the correct count. But of course, the problem is, what if we don't have one leader? We have 0 or more. So we need 2 additional techniques. We run this procedure in many parallel threads, in a number, I would not say many, I think it's logarithmic, in a number of parallel threads. And we check whether there is a leader or not in each thread. So if there is no count at the end of, remember that this is synchronous and it runs for so many rounds. At the end of the execution of methodical counting, if there was no count, there is no leader. Therefore, we know that in that thread, there was no leader. If the number of threads without leaders is more than half, there has to be one of them which has exactly one leader with high probability that we show in the analysis. Right? So again, leaders choose with this 1 divided by K probability to be leader. Nodes choose with this 1 divided by K probability to be leaders or not. If k is close to n, there is a high probability of having one of these threads with exactly one leader. Yes, sorry.
The threads are subsets of nodes, and they choose.
No. Every node runs so many threads. So imagine you have so many networks running the same algorithm at the same time with the same estimates and everything, right? But the stochastic choice in each network is independent. In each network is independent. Therefore, in one network you have no leaders. In another network you have 25.
They choose to be leaders or not.
Exactly, independently in each thread. Sorry about that. I should have said that.
You might have
So
said it.
basically, the more thread you have, the larger your message size.
Well, there is a message complexity, yeah, because you send messages through every thread. But it's a logarithmic number of threads. It's not difficult to, yeah. If the number of threads without leaders is more than half, we show in the analysis that at least one thread should have exactly one leader. And that is the count that we want to use. However, how do we know which one, right? We run, and in many threads, we get a count. When we end, we get a count, but which one is the one that corresponds to exactly one leader? Well, we showed that if there is exactly one leader, the count is larger than for more leaders. And therefore, we choose just the maximum. The node runs many parallel threads and gets some counts. If more than half of the threads don't have any count, you just choose the maximum of the other threads, and that's the correct count. That's the way that we solve the issue. Well, if that is the correct count, if capital K is bigger or equal than n. If not, because the algorithm continues, at some point, capital K will be bigger or equal than n, but of course, this is, it doesn't terminate. Well, with these results we published in ICAL 2019, we reduced the methodical counting to multi-counting, reduced by 1 the exponent. So the speed up is n times L divided by log. So more leaders, faster the algorithm, because now we divide by L. It's n to the 4. Before it was n to the 5, now it's n to the 4 plus some arbitrarily small constant, and divided by L.
At some point, if you keep doubling this big K,
It's going to be too
choosing
big.
this random.
Too big.
Yeah, like that's going to be the biggest.
There are
cost of your
physical
algorithm, right?
limitations.
So what
Yes.
you.
There are also we are working now in that. There are also physical limitations in the averaging of potential.
Mhm.
The precision of this division is exponential, right? So yeah, there are limitations, and we are working on that. I'm going to refer to that later. And well, for the randomized algorithm, we also obtain a similar speed up, and that is the first one without leaders. In this whole area of study, is the first one that works without leaders. But it is unconscious counting. It's not the original problem anyway. This is a summary of the work that we did on this line. This was the initial work with Alessia Milani in Bordeaux. Then I worked with Darek. We got ICAL 18 and ICAL 19, the papers that I presented today. Then we have follow-ups with students. I have students working with me in various simulations of all these algorithms in different settings, stochastic networks, adversarial networks. Now I have a student working on implementing this on a parallel machine on GPUs so that we can scale the network size, because it's very computationally intensive because it changes the topology in every round. So for simulation purposes, you need to generate a new topology in every round. And for some, for instance, uniform, unrooted, unlabeled trees, to draw uniformly from the space of unrooted, unlabeled trees is very computationally intensive. So we are trying to parallelize this to be able to speed up, to scale up the network sizes that we are testing. And we have follow-up works, theoretical works also, on, as I said, on leader election and network consensus. Rebecca asked me to do an overview also of my areas of research. So this is a quick overview. This is what my I would say 50% of my focus is on ad hoc networks in challenging conditions, right? Communication and computations. It's been since my PhD thesis already. And I have some work, or a lot of work, I would say, on crowd computing, applying game theory with other people, with other collaborators. More recently, I've been working also, here. I've been working also in 5G cellular communications, scheduling of packets, and also spammability and fairness in web ranking algorithms like PageRank. I work on these areas mainly thanks to my collaborators from many different universities. Some of them you may know. And by those collaborations, I'm able to expose many of my students to international research, which I think is a great experience for them. They usually are amazed by these interactions, although of course, most of it is remotely, right, online, either because of the pandemic or because of costs, but they still get exposed to this. They get to simulate algorithms that are at the forefront of research, and it's a very nice experience for them. Most of these are undergrads, except this is my PhD student and this is my master's student. The others are undergrads, and it was the first experience for them, and it was great. Marty is now working on applications of this algorithm to vehicular ad hoc networks, and Krutika, some of them graduated and went to industry. But for me, it's really, I enjoy a lot working with undergrads. And the problem is that the time frame that they have is not long. So I don't get them to work on theory, on the theoretical aspects, because it could take 6 months or 6 years, you never know. But the simulations are more concrete, right? So I put them to design the simulations, run the simulations, analyze the data, and for them is an amazing experience. And I always tell them, you never know how. Even if you're planning to go to industry, it may be very useful to have a paper published. I always ask them to, we go for the paper, right? The paper published is a good, for your resume, and later on you may decide to go to grad school, and who knows. About follow-ups, which address what your concern, we are thinking of models. Actually, we already have results in the first 2 bullets. Models with less connectivity. So we have one interval connectivity. What if the network sometimes gets disconnected? What if this is mobile and gets disconnected? We establish a model of this connection, and we prove new results. And we still need to write the paper, but we are going to be submitting soon. What about limitations on communication? We are also working on the so-called congest model, in which each node can transmit only log n bits in each round. And we also have results on that area. Of course, we are working on reducing the gap between upper and lower bounds, which is still large. Dynamic diameter lower bound, and to the 4 upper bound. Other computations beyond algebraic and asynchronous protocols, meaning in our protocol, every node has to start up and start running at the same time and follow the same rounds of communication. That is rigid to a model, for a model like anonymous dynamic networks, where you have weak assumptions. So we plan to work. We didn't start yet with asynchronous protocols, but we also plan to work on that. And as I said, we are looking at other models of communication beyond this one, like in nano networks. Usually, for instance, one of the probably possible models of communication in nano networks is called molecular communication. They exchange only by passing by molecules, only exchange a little bit of information by passing by next and to each other. Over there, what you have as a tool is the geometry, right? That is a geometric network. In our model, it's completely adversarial, so a node can become the neighbor of a node that before it was far away. Adversarial, it says. That adversarial model is quite hard. That's why we have Alex, my master student, working on stochastic networks as well. And that is it. I hope, yeah, it was a little long, but
Thank you.
thank you. Any questions?
Answer?
Yes. So curious about the motivation for the anonymous part of the anonymous dynamic.
Mhm.
What's the situation? You know, we drop all our nodes in a volcano or whatever. We should know ahead of time which nodes we have. When does this need to be anonymous?
The anonymity is about the identifiers.
Right.
So there are different, I have read in the literature different ways of motivating this, but the one that I think is more appropriate is, you're deploying a massive network. And in order to use the identifier, you need them to be unique. And if it is massive, for starters, the length of the identifier could be too long, but it's still log n, right? But it may be impractical. It may be too expensive. You think of this at the nanoscale, and this have to be very, very cheap. And for applications like molecular communication, well, molecules don't have, I guess they have, I'm not a biologist, but it's not a unique identifier that we can use easily in an algorithm. Basically it's that, the massiveness of the network. And that's why we are so interested in scaling up the simulations, because our simulations so far go up to 100 nodes. And that, of course, doesn't make sense for a network of massive size. Well, what massive means, of course, is ambiguous, but we would like to go to 100,000, yeah, at least.
So if I followed correctly, it seems like at least some of your algorithms, the one where they kind of keep going, and once they find the right answer, they stick to the right answer,
Yeah.
Have built into them a certain amount of self-stabilization if the wake up at least is asynchronous, right? So you can, maybe you still assume once a node is awake, it's permanently awake and it sends it the right kind of rounds and has the other assumptions, but that if, basically if the count is, and maybe it even works if some are dropping out, but it seems like as if they come in later, they'll be detected once they come in.
Yeah, as soon as you remove this, everyone finishing at the same time and obtaining the correct count, I think that kind of scenario is possible.
Mm-hmm.
Yeah, because the algorithm is very resilient,
Mm-hmm.
right? It's not
Right.
the technique is
Right.
well known. It's gossip and it's very resilient. You keep sharing and sharing and sharing. Sooner or later, you reach the correct count, even if some come and go.
Mm-hmm.
There is an issue for counting, which is we need even to define what we mean by the network size if the nodes come and go, which is, I guess we can establish some average over so many rounds or something, and that's what we want to compute. It's going to have a delay. If there is a lot of dynamicity, it's going to have a delay, meaning I will be able to compute the average size over so many rounds later, right? But yes, all that is possible. Yes, definitely. I think this gives room for a lot of variants, right? And studies.
Yeah. And I mean, I think algorithmically, they're all interesting questions. I do think coming back to like, what are the characteristics of the actual networks of interest?
Yeah. Well, you read the news the same as me. I mean, there are all the time these new networks being designed for Internet of Things and so on. The nanoscale, they used to call it in the past smart dust, right? They are still not implemented. So for now, everything is exploratory. But yes, lots of questions with small differences in the model brings a new array of questions. Yeah.
Any questions in the chat? Or
Chile, any question?
okay, good.
That's one more question.
Yeah, go ahead.
Yes.
So on one of these slides, there was something about you could tell if you had gotten the number, the k correct, if you were within k n plus 1. There were these thresholds.
Yeah.
I can't remember. So is this an issue though? If you've got yes, that's the one. Yeah. now, K is massive, 100,000. Do these bounds, are they harder to hit, or these are just absolute bounds, it's not sort of a distribution?
No. This is deterministic. Yeah. It's K minus 1 is the total potential in the network, right? Because each non-leader has a 1 and the leader has 0. And there is only exactly 1 leader. Remember, this is the initial work.
Right.
So they should not get more than K minus 1. If they get K minus 1, potential was created, which is possible, but only if K is smaller than it.
Right.
The lower bound is K minus 1 minus 1 divided by K. It's a small fraction smaller.
Yeah. Thank you.
All right. Great.
Thank you.
Thank you again.
Thank you. I hope you liked it. Thank you, Chile.